Welcome. In this video, where we are going to extract depth map from a 3D Gaussian splatting. So what is great with Gaussian splatting, of course, is that it's a 3D representation of the scene. So what you can do, you can splat them or generate images. As you see here, you have a few examples of images, but you can also extract a lot of other things. For example, you can extract depths. On that do not require any modification in the training pipeline. You can take any pre-trained Gaussians, and you can do a lot of things with them, including extracting the depths, okay? So in this video, we're going to have a look at the code, or we can do that from a code perspective, and you will see that it's very easy. We only need to change one line of code, okay? So we're going to start with this code. I will put the link in the description, but basically it's the code we implemented in one of my latest videos. We implemented 3D Gaussian splatting from scratch, in PyTorch only, so no C++, no CUDA. It's of course a bit slower than the official implementation because we just use PyTorch, but in terms of quality, we have metrics that are on par with the official paper. So it's state of the art in terms of quality. Of course, it's slower, but at least we have a self-contained code. Everything is in a single Python file. It's very easy to understand and it's self-contained. So what we're going to do, we're going to copy-paste this code, and I'm going to show you how we can modify it to render the depths. So basically, Gaussian splatting, so it takes an image, it takes Gaussians as input, it splats them and creates an image. What we splat here is the color, so each Gaussian is a property. Well, it has many properties, but one of the properties we are interested in is the color. But what we can do, instead of splatting the color, we could splat anything. So for example, what I can splat is the depth of the Gaussian. That will give me a depth map. I could give some specific attributes to the Gaussian, and I can do that post-training again. And what I can do, I can splat those properties. So here, what we want to do, we want the depth. So basically, what I want to do, here I have the color. I will just need to replace the color by the depth. Here it's z. So the project points function, what it does, we can have a look at it. It takes the Gaussian positions. So PC for position. On it, first it goes from world space coordinates to camera space coordinates, and then it also computes the u and v, so the pixel coordinates in 2D space. Okay, so basically where the Gaussians are in the image in 2D. But here what we care about is z. So basically it's just the position of the Gaussians in 3D space, but from the camera coordinate system. We want from the camera coordinate system, not from the world coordinate system. And basically we're going to the attribute of the Gaussian that we want to splat is the depth. Well, it's z. So z gives us the depth, well, the distance between the camera and the Gaussians. So basically here we just want to splat this attribute, so the depth. So because our code here is made so that it splats the color, we're just going to override the color. We're just going to say color, it's equal to z, okay? So in this code, in this implementation, it was not generic. It was made so that it splats the color. We could make it a bit more complex so that it's really generic, and we can give any attribute we want to splat. But if I do this trick, I just replace the color by z, so the position of the Gaussians in camera coordinate system. So basically z tells me the distance between the camera to the Gaussians. That will work. Here for the code to work, because the color is 3 channel and z is only 1 channel, what we need to do z.expand, so 3, z.shape of 0. So basically I'm repeating z 3 times so that it matches the shape of color, or the expected shape of color, because in our code we assume that the color is 3 channel. We need to have z to have 3 channels, okay? The shape of color is n number of Gaussians, 3. Here the shape is 3, number of Gaussians. So one last thing we need to do is to transpose the results. So we do .big-T to transpose the results. And now we can run it. It will give proper results. What we could do again is to make the implementation a bit more generic. so that we don't need to have specifically 3 channels. We could just make it work so that even if you have only 1 channel, it works. That will be easy to do. Here I'm just showing you, or you can quickly hijack the code in some way. You can also do that in other implementation, for example, in SplatFacto, in NeRF Studio. Of course, NeRF Studio already allows you to provide flags so that you can compute the depth. But let's say that you have specific properties for your application. You can easily hijack the code to splat it and to generate a map of what you need. Okay. One last thing we can modify at the end of this rendering process. We are clumping the image between 0 and 1, because pixel colors are between 0 and 1, but here we are no longer rendering a pixel colors, we are just rendering depth, so I'm removing that, okay? And then you can run this code, it will run on the fly, you just modify 2 lines of code, and you are able to extract the depths from the Gaussian, from the pre-trained Gaussians, okay? I hope this video was helpful to you. I have more videos on Gaussian splatting coming up, so please subscribe if it's not already done. Like this video, comment, even a simple comment, just hello. It's really helpful with the algorithm. As a reminder, I have a course on 3D Gaussian splatting, where we really dive into all the details of Gaussian splatting, from the end of the camera calibration, so call map, to the training and to the rendering of the Gaussians. So if you want to learn that, I invite you to have a look at the link in the description. Thank you.